Looking for a great portable radio? Then check out TECSUN on our website.
TECSUN 501X.
TECSUN PL990X.
TECSUN PL680.
TECSUN S2000. TECSUN 330.
TECSUN S880GM.
Hello and welcome once again. I've entitled this video HF Antenna Mystique. Why? Well, because I still get a lot of emails from hams, particularly newcomers, who are really not quite sure about antennas, and they talk about, will this antenna give me gain, and is this antenna better than that antenna? Quite understandable inquiries, but some of this is born out of Mystique. Now when I say Mystique, I think that the CB market was very prolific at one time in giving antennas names, all sorts of names which conjured up sort of fearsome antennas that penetrated, that sort of thing, antennas that had a lot of gain. And in the ham radio market, of course, we've still got the high gain antennas that we import from the USA. High gain is spelt H-Y-G-A-I-N and not H-I-G-H. But quite clearly the name high gain was intended to create some sort of power over that antenna that had some sort of gain over another antenna. It's rather confusing, really. I mean, I can go back to some of the really early days of antenna Mystique. In fact, I did a video about the joystick. Partridge Electronics manufactured something called the joystick. Yeah, I've got a copy of, in fact it's a copy of an RSGB publication. It's an RSGB call book, and in that RSGB call book you'll see here a full page advert for the joystick antenna. Now it was a very popular antenna. The joystick gave it a sort of a connotation of, I don't know, it was going to work, it was going to give you joy. And it was very popular, and lots of ham radio operators used it. And believe it or not, despite its size, it was very popular for 160 metres. But really and truly, one of the, I won't say the secrets of it, but the main radiating part of the antenna was not the antenna, but it's what Partridge Electronics called the feeder. The feeder was actually the part that radiated mostly. I mean, there was some radiation from the coil at the far end, or joystick at the far end, which was a little more than a broomstick with a coil on it. But anyway, it was popular, and it appeared in the RSGB call book one year. But you know, putting names on antennas does cause a little bit of mystique. It causes the would-be customer to think, well, that sounds a nice name. The Penetrator, the Thunderbolt. If I just called it the XYZ123, would it have the same effect on sales? No, I'm sure it wouldn't. You know, over the years of ham radio, there's been all sorts of antennas for the HF bands that have been invented or designed. I'm not sure what the right word is, designed probably. If we go back to the 1950s, there was the G4ZU mini beam. Now that was a very famous antenna in its time. It covered three bands, 20, 15 and 10 metres. As its name suggested, it wasn't a full-size antenna on the lowest band. On 20 metres, it was certainly much smaller. I think the dimension of the longest element was about 22 feet, but it covered 10, 15 and 20 metres, no traps. And I may well actually revisit that antenna at some time in the future because it's quite an interesting antenna. It was certainly very popular in the 50s and 60s. And it was designed by a guy called Dick Bird. Now I'm not sure whether his Christian name was Dickie, but anyway, he was known as Dickie Bird. G4ZU designed the G4ZU mini beam, but he also designed a couple of other antennas that I recall. He designed something called the bird cage, which actually was a quad, a metal quad. I can't remember the details now. I'm sure if you throw it around on the internet, you will find it. The G4ZU bird cage, and also designed something called the FB5 dipole, the ferrite bead dipole, and that was basically a dipole. I think the dimension was around about sort of a full half wave on 80 meters. But he threaded some ferrite beads into it, and if these ferrite beads were put in certain positions, it made the antenna multi-band. Now I can't recall again the details of the antenna and what the SWR was, but it was a multi-band design. And then we had W3DZZ, the American guy who designed a fairly simple 5-band dipole. That was basically again, it was a trap dipole. The lowest band was 80 meters, and it used a pair of 40-meter traps. And if you had got the LC ratio right, it claimed that you could also run it on the other bands, so it covers 5 bands, 80 through to 10 meters. And of course we have the G5RV, probably the most famous antenna of them all, designed by Louis Viney. Now I will revisit that antenna in the next video or so, because there's a lot of things about that antenna which perhaps aren't always appreciated, and it's had some bad press, it's had some good press, but that design goes back to the late 1940s, after Louis Viney came out of the services. He was involved in radio design during the war, and a very successful engineer. Came back to Marconi's, but as I say, the G5RV was his design, and we will revisit that in some future video. But it has to be said that there is no silver bullet antenna. There is no HF antenna that stands head and shoulders above all others. And if there was, by now it would have been discovered. So sorry to disappoint you, but there is no silver bullet. But it doesn't stop us discussing HF antennas and some of the mystique. Any bit of wire or bit of tubing will actually radiate. It'll work as an antenna. Now I've seen in the past people say, oh, this antenna's no better than a dummy load, which is a derogatory statement and clearly wrong, because any bit of wire and any bit of metal will radiate. And the trick really is getting the maximum amount of current flowing through that bit of wire, that bit of rod. Provided you can match that rod, which means, say, you get the transfer of energy from the transmitter into the rod at its maximum, then you'll get the maximum performance of that bit of wire and that bit of rod. The secret is getting the maximum amount of current flowing through the element that's going to radiate. Now, quite clearly, there are certain parameters that need to be met. For example, I could have a matching system that would match 20 meter, 40 megahertz energy into a rod that's just 2 meters tall. It would work. It wouldn't work so well as a rod that was twice as long. If I made it 4 meters long, it would work a lot better. The efficiency, the transfer of energy into the ether would be a lot better. So there are certain parameters that need to be met. But basically, as soon as we start to change the length of a wire or a bit of tubing, two things happen. It might start to become a better radiator, but it also changes the actual pattern of the antenna. In other words, the way that the energy is dispersed, the actual polar diagram of the antenna. We could make the antenna such that it fires in two directions in a very narrow beam, or we can make it fire with lots and lots of lobes. So the actual length of the antenna is quite an important feature, and that really is part of antenna design, manipulating the length of the antenna, the size of the antenna, to create the diagram, the polar diagram that you need. A vast number of antennas are based on the simple dipole. The dipole is the basis of a lot of antennas. And we can look at Yagis, which are multi-element antennas, but basically they're fed with a dipole or a variation of a dipole. We can look at verticals, but even a vertical is basically a dipole. You've got half of the dipole poking up in the air and the other half is basically the ground beneath it, or the radials. So the dipole is a very essential part of antenna design. And really and truly, it's the variations which people have used to create all sorts of different antennas with all sorts of different claims about how good they are and so forth. And then they sort of blur it a bit by giving it a name, and we all think, oh, that's great, that's a wonderful antenna, and somebody tries it out and says how wonderful it is, and we've got another winner for a little while. We've been modelling antennas now in software for quite a few years. It's very easy to do. You just load the software up on your laptop and you can draw yourself a dipole. You can see the radiation pattern of it. You can draw yourself a vertical antenna. You can see the radiation pattern of it. And you can play about with the height of a horizontal wire and see how the angle of radiation changes. You can see how the feed point impedance changes. It's very absorbent. And it doesn't take you too long to realise that if, for example, you have a vertical antenna, it gives you very low angle of radiation. It's great for DX. The angle of radiation is very low and it travels a long way before it hits the reflective surface, comes back down. Great for DX. Same with the dipole. As you raise the dipole, you get a lower angle of radiation. It's great. What could be simpler? As useful as antenna modelling is, it does tend to give us exactly the same results that have been in the textbook for years. I mean, I've got an example here of a ARRL antenna handbook, which has got all the polar diagrams in there. A little publication by the RSGB in the late 1940s. Again, it shows diagrams. So antenna modelling, a lot of the time, is simply telling us what we already know anyway. The problem is that antenna modelling doesn't actually tell you the truth. It tells you what could happen, but it doesn't tell you what does happen in your garden. The reason being that your garden, your location, has a big effect on the performance of the signal. I published a video fairly recently, The Mystery of the Vertical Antenna Solved, and I gave you an example of pedestrian mobile operator in Spain working VK, ZL, putting out CQs and getting calls back from the Pacific. The secret was he was operating right on the edge of a saltwater stretch of water, lake or whatever it was. And it's very impressive. But that same antenna wouldn't produce anywhere near the performance in your garden. And the problem with modelling is that whilst modelling can take into effect the ground beneath the antenna, you can feed in some data and you can allow for the ground conductivity and so forth. What it doesn't do, it doesn't take into account what we commonly call the Fresnel zone. Now the Fresnel zone is a zone which extends quite a few halfways beyond your antenna. Not just 10 or 15 feet or the length of your radial for your vertical. It extends quite a few full waves from the antenna. If you look in your average garden, you'll find that you've got houses, you've got telegraph poles, you've got power lines. All the houses are laced with wire for power lines and earth for power cables and earths. You've got trees, you've got shrubs, you've got all manner of objects which are in the way, and they're in the way of this low angle radiation, which is why so many people find that a vertical antenna doesn't work quite as well as they hoped. And I've proved this myself before, and I've covered it in the video. Time and time and time again over the years, I found that my vertical antenna doesn't quite work as well as I'd hoped it would work. And it's because of the surrounding area. Now, if I put up a vertical antenna in the middle of a field and put some few radials around, it would work quite well. It would come fairly close to what I expected and what the modelling suggested. But if I put my vertical antenna into a typical small garden, it certainly won't work anywhere near as well as the modelling would suggest. But there's nothing you can do about it. You are stuck with the garden you've got. And as I've said again on previous videos, you've got to make the best of what you've got. We would all like to stand at the edge of a salt lake or salt water ocean and put out very good signals because of the great ground plane we've got, or the great reflective area we've got. Same with horizontal antennas. Wonderful signals, but we don't all live. In fact, not many of us do live right near salt water. So we have to accept it. We have to accept that we're not going to get such good performance, but we will get the performance that we are able to get, and we have to accept it as a bit of a challenge. And it's comforting to know that the majority of us operate from small gardens. So, okay, fine. We would like to have a massive, great fishing rod and throw it out to sea and get lots of fish. But we've only got a small fishing rod. We've got to make do with a small fishing rod and perhaps not so many fish. Fact of life. If there was a silver bullet HF antenna, it would have been invented and we'd all be using it. We're not. We all have our own personal choices of aerials. Horizontal or vertical sometimes and very often depends on the location, what we can and can't get up. But most antennas, most doublets, most dipoles, most verticals work quite well. They may not work as well as you would hope, and perhaps I've covered this with verticals and with horizontal antennas. You can't get up as high as you want to. Again, we are stuck with it. What you need to do is to make sure you match it correctly, and in matching it correctly you'll get the maximum amount of current flowing in your antenna. And if you get the maximum amount of current flowing in your antenna, then you can't wish for much more than that. In fact, back in the old days we used to use current meters. I think MFJ still makes some current meters, but if you had a current meter in the element of your antenna and you adjusted it for maximum current in that antenna at a given point, then you've got the best you can possibly hope for. But before we finish, let's talk about antenna gain, because that does cause a lot of confusion. I've been asked on occasions, what is the gain of a mobile antenna, HF mobile antenna? Somebody said to me, the diamond 20-meter width, what is the gain of it? Well, it's a logical question if you're a newcomer to radio. A decibel is the measure of gain. A decibel is the smallest amount of change in signal strength or audio that the human ear can detect. If we double our power from 100 watts to 200 watts, we have a 3 dB gain. If we multiply our power by a factor of 4, in other words, we go from 100 watts to 400 watts, we have what we call a 6 dB gain. 6 dB is 1 S point. 6 dB is very worthwhile. But 6 dB is roughly what you might get from a 3-element Yagi. You may get a little bit more, perhaps 7.5 dB. So if you increase your power, you make a big difference to the signal strength at the far end. So gain is worthwhile, but gain is a reference. A decibel is not a measurement, rather like volts or current is. dB is a comparison. So if you're talking about gain, you've got to compare it with something. And in general, you compare it with a dipole. A dipole is, as I said before, is a very common aerial. If you use for horizontal antennas, that is, if you use a dipole as a reference point, then we can say, okay, if we add an extra element to the dipole to make it a 2-element Yagi, we get 3.5 dB gain, maybe 4 dB gain. If we add an extra element beyond that, we get 3 elements, we can get something like a 6 or maybe 7 dB gain. That 7 dB gain can also be added on to the DX gain. DX gain? What's DX gain? Let's imagine that we have a half-wave dipole on 20 metres. It's 5 metres above the ground, and because it's only a quarter wave above the ground, it has fairly high angle radiation. When the energy leaves the antenna, it travels at a fairly high angle, hits the reflective layer up in the air, comes down at some remote point, and if we're based in the UK, we can expect to get good signal reports around Europe. If we raise that dipole from 5 metres to 10 metres above the ground, that means that our 20-metre dipole is now a half wave above the ground. And at that level, the angle of radiation has reduced significantly. So the energy travels further before it hits the reflective upper layer, and then comes down at some remote point, somewhat further away. So it could be in Asia, or it could be North America. So we've actually increased our signal as far as DX is concerned, and that can be something like a 5 or 6 dB gain. So if we add that 6 dB or so gain, it's arbitrary, 6 dB gain to, say, our antenna, which has already got a 6 dB gain, we've got a 12 dB total gain. So Joe Bloggs down the road, who's got this 20-metre tower with his 3-element Yagi on top, lucky fellow, has probably got a 7 dB gain from his Yagi and at least a 6 dB gain for DX. He's got a total of about 13 or 14 dB. Good for him. Not such good news for you, of course, but that is a fact of life in ham radio. So when it comes to antenna gain and trying to understand antenna gain, we can regard a dipole as the basic reference point, the 0 dB. And if we add elements to it to make it a Yagi, we increase the gain and we add dBs to it. What happens if we reduce the size of a dipole? Perhaps reduce it to half size by adding loading coils. Well, it actually doesn't make too much difference to the actual radiation efficiency of the antenna. There will be a small amount of loss, but it's not much at all. What does happen is that you reduce the bandwidth of the antenna. So when you start to move around the band, you find the VSWR increases much more than it would do if it was a full-size dipole. So reducing the size of a dipole doesn't make too much difference, but it does restrict the amount of movement you can make before the VSWR rises above an acceptable level. So a full-wave dipole is our reference. Verticals, well, quarter wave vertical really is the reference, I suppose. Quarter wave vertical is a common antenna these days. Again, if you reduce the antenna, you can reduce the vertical by about half the size by adding a loading coil. Again, it doesn't change the efficiency that much, but again, it reduces the bandwidth. If you increase the length of your vertical, then the angle of radiation starts to change somewhat. It's rather complex. We won't go into that now, but basically regard a quarter wave vertical as a reference point. So if you've got a short vertical on the car, say for example you've got a 40 metre vertical which is only 2 metres high, whereas it should be, what should it be, 10 metres high, shouldn't it? To be a full size. So there was obviously quite a reduction there in efficiency and very much reduction in bandwidth. If you increase the size of a dipole beyond a half wave, then the pattern starts to change. You get gain in certain directions, but you get nulls in other directions. Again, it starts to become quite complex. And if you want to explore this, then of course you can model it in software, but with the reservations that I've already mentioned. So why have we got so many different designs of antennas? Well, a lot of the reasons for having different antennas is because we want to make them multi-band. So you can have trapped dipoles, you can have trapped Yagis and so forth. And the reason for all these different designs tends to centre around trying to make the antenna multi-band, and that is rather a complex field, but there's some pretty basic antennas out there. We've covered the G5RV, but we'll cover that in greater detail in another video. What I'm trying to impart is the fact that antenna science has been well developed, well explored, and there isn't this sort of silver bullet. A dipole's a dipole and vertical's a vertical. And there's not too much you can do to change those apart from alter the position of them or to move to a different location, which is rather radical. But one final note, when you're erecting an antenna, do pay attention to the feeder cable, the coax cable. It's very easy to get yourself in a bit of a tangle simply because you haven't connected the coax plug correctly. When you're putting plugs on coax cable, there's plenty of guidance on the YouTube channels on how to put a PL259 plug on, which is the common plug, or perhaps an N plug. do watch those videos, and also do check after you've finished installing the connectors with an ohm meter, an ohm meter, because you need to make sure that first you haven't got a short circuit, so you can check that very easily by making sure the coaxium is not connected to anything, and then connect the meter across from the centre pin to the earth. You should have an open circuit, and then check that the centre pin at one end of the cable is connected to the centre pin at the other end of the cable on the connectors, and also make sure that the outer sheath, the earth side of the connector, is connected to the connector at the far end. Those two basic checks are really essential before you connect the coax cable up to the antenna. You'll be surprised how many problems stem back to faulty plugs, or not faulty plugs, but plugs not correctly connected. And I suppose really when I finish this video I should say what I use. Well, I use an end-fed half-wave at the moment. I've been using an end-fed half-wave wire antenna for some while now, and if you've watched some of the videos you'll realise that I rate that better than a vertical for a small garden. Now, I'm not saying you shouldn't use a vertical in a small garden, because sometimes you haven't got much choice, but I do find that the horizontal wire beats the vertical, and I've covered that in various videos and given the reason why. But if you check the video about the mystery of the vertical antenna, which I'll put a link to at the bottom of this video, you'll get some idea. So there we are. That's the video about the mystique of antennas. It's, you know, HF antennas in some ways are very simple, and in other ways they can be very complicated. But if I produced a dipole and called it the Peter Waters 123, yeah, fine, it works as a dipole. If I called the dipole the penetrated dipole, or the high gain dipole, you might be fooled into thinking that, well, that must be something a bit different. Well, a dipole's a dipole, so don't get sucked in by names. And by all means read some of the basic books on basic antenna design and so forth. And yes, if you feel inclined to experiment with the software for modelling antennas, it's great education. But do bear in mind that the answers don't always translate into practice, certainly when it comes to the actual polar diagrams and so forth. But there we are. So enjoy the ham radio. Take care. Ham radio is a great hobby, and ham radio is all about experimenting. So don't be frightened to experiment with antennas and try them out if you wish, but just sort of keep a fairly sort of open mind on some of the claims. In the meantime, thanks for watching this video. Don't forget to press the subscribe button, and speak soon again.